Okay, so this is section 1.1 from the book. It's just basically an intro to statistics. Okay, so basic terms for statistics. So this whole first chapter is a list of terms, basically, and when I test you on this, there's going to be a lot of multiple choice and maybe some fill in the blank stuff. Okay, so statistics is basically, before I jump into the terms here, statistics, it's basically generalizing from small sets of data to I guess I should say representative collections of data. So I'm going to go ahead and use the official word, representative samples of data. To large populations. So it's not just analyzing data, it's a little more complicated than that. It's that you want to learn about some big population, but it's so big that you couldn't ever really study it completely. And so what humans do absolutely all the time is they look at representative subsets that we call samples. And then we say, well, if 59% of people in the last election voted for someone besides Trump, and that's based on 1,000 people that I gathered sort of randomly from all over the country, then I'm going to estimate that 59% of people in the whole, of all voters. So you see how I generalize from this small group to a whole population of voters. And when you do that, you're sort of making what they call an inferential statement. You're making a statistical inference, which is basically sort of an educated guess based on data that hopefully are representative of whatever population you're talking about. Okay, any questions yet? And you can see just saying that it sounds problematic. Generalizations in general are tricky business because sometimes, because again, you're going from specific cases to large sweeping statements about things that you really don't have a lot of, maybe you don't have complete information about, but you're still talking about this as if you know what you're talking about. And so it's always a little tricky. Generalizing is just another word for inferring, where you are making sort of an educated guess, hopefully. All right, so then some basic terms. Datum is one piece of information. Nobody ever uses this word. So if I have your height, I could say this datum is quite impressive. One piece of information. Nobody says that. You'd be a total nerd if you said datum in any situation. But data, of course, is plural for datum. And so that, statistics nerds really want you to say the data are as follows, not the data is. And that's what I'll do because I'm a statistics nerd. Okay. So, you would say the data are misleading. Oops, except for I can't spell it.
What, Professor?
Yeah.
Would it also mean collection of observations?
You mean data?
Yes.
Yeah, of course.
Okay.
Just if it's information, I mean, call it an observation, but it's still information, right? So it's all good. Population is a large group that is of interest. But too large to study completely. If it's not too large, technically you're not doing statistics. So in this context, it's too large. And then a sample is a subset of a population that is representative of the population. I'll say of it. It should include all types of population members. Now I'm going to use that sort of loosely, whatever it means. Oops. And I could go deeper into this, but to be representative means you're not going to get everybody in the population, but you might get all kinds or all types, and whatever that means. And it would be, it just depends, right? I mean, if you're trying to do a survey of voters, then you shouldn't just, of US voters, then you shouldn't just collect people from California. So including all types might mean, you want to balance it out in terms of gender and race and probably political party and the state that people live in, and even, where in the state. So you're just trying to go all over the country if you're doing a survey of American voters. Okay, any questions? Okay, then a parameter is just a numerical measure. Oops. Or maybe a summary value of an entire population. Okay, so we could talk about a population mean, or maybe I'll say an average. So I'll just keep this informal, like an average. Or a percent. Okay. And then a statistic, so the idea is you can't know the value of a parameter because requires you have data for a whole population. So parameters are usually unknown. Okay. A statistic is what you have to use instead. So this is a numerical measure. Or summary value. From a sample. So used to estimate a parameter, and I'll say an unknown parameter. Okay. So it's easy to forget what the word parameter means. I use it from time to time, but obviously you'll all remember what a statistic is. So if I talk about the mean age of all voters is 40 years old in the US, if the mean age of voters is 40 years old, is that every voter in the country? If it is, that's a parameter. But the fact is nobody knows what the mean age of voters is because I just don't know that all those numbers are collected in a single database. If you could do it, then you'd be able to get the parameter, the measure of an entire population. But normally you would do it from a sample. You just get a collection of voters from all over the country, of all parties, political parties, probably, in proper proportion. So if 5% of voters are from the Green Party, then it would be nice if 5% of your sample had those same number of Green Party voters, like that. Okay, any questions?
So I know this is kind of off topic, but I forgot to say that before. So is it okay if I make a group chat for this class?
That's fine.
Okay, so I'm going to send a link in the chat box so everybody can join.
That's great.
Okay, thank you.
Okay, next, just a quick little example. It says researchers surveyed 1,000 randomly selected California high school students, asking them if they've ever carried a gun on campus. 13% of students admitted to carrying a gun on campus. That seems like a lot. Okay, so what's the population here?
1,000.
California high school students?
Is it 1,000 or is it all California high school students?
All?
Yeah, so this would be all, because the population is the large group. Okay, so this would be all Cali high school students. Okay, what's the sample?
1,000 students.
Yeah, that's the 1,000 students. Good. What's the parameter?
Would it be the 13%?
Well, so now think about this. Do you think that that 13% comes from a population or from a sample?
From a sample.
So what would the 13% be? Is the 13% a parameter or a statistic?
Statistic?
The statistic.
The parameter, would that be the gun?
Now remember the parameter can be a percentage, but you probably won't know it. See, the problem is if you know the number, then it's probably a statistic, because nobody's going to ask every high school student in the state of California if they've ever carried a gun. It's just too many people to ask, and they're hard to get to because they're everywhere. So for the parameter, this would just be maybe I should say the unknown percent. That's wanted. I don't have enough room to write much more here. Okay, but the statistic is the 13%. That's used as an estimate. Yeah, I'll go ahead and be a little more thorough on this answer. Used to estimate the percent of California, California high school students who've carried a gun on campus. Normally when I put a figure out like this, I get some sense of what the real value is, but I think that 13% is absolutely bogus. I'm guessing, I hate to say it, but I'm guessing I just made that 13% up in the example. So the whole thing's fictional. You guys okay?
Could you open the chat box for everyone so I can send it to everyone, the link?
Not right now, because that requires me to go back to the Zoom and change my settings.
Okay, so we'll do that later. Thank you.
Yeah, no, if you just send it to me, just send it to me.
Okay.
And I'll send it back to the group. I think I can do the whole group. And then I'm gonna keep going for now. Okay. So for error, let me box this. Who is that?
Oh my God, I'm so sorry.
We heard you. Okay, so error is just okay, there's the link. So y'all, I'm just gonna copy this over to you guys. I don't know if it let me do that. Copy, and then let's see if I can message everyone. Okay, you guys, so I'm not endorsing that link. It's not from me, but you're welcome to use it. Okay, so for error, this is just the difference between a statistic and a parameter. So this is error is the difference between the statistic that's an estimate and the parameter is the true value you want to know. Okay, but you don't know it. Okay, so again, parameters are typically unknown. And error is sort of the thing we need you guys to really grapple with in this class. If you remember this notion that error, everything you do is an estimate and therefore it will have error. That is, you're working with sample data and hopefully your sample is representative of some population, but that doesn't mean your statistics are going to be exactly right. They will not be. And the way that you get this estimate kind of is very closely related to how big your errors are. So we have to do statistics in a way to minimize error, but even having done that, we need to be aware that our statistics contain error, and error can lead you to make bad decisions, and even to mislead people. So we don't want people to be misled. We need to be honest about our error, and we need to be absolutely aware that when we read research, that sometimes it's wrong. And so we we just really need to be sort of knowledgeable about that. And sometimes our own research is wrong, even when we do it right. Okay. So descriptive statistics, this is just summarizing large data sets. Using, statistics. And maybe I shouldn't say statistics when I'm defining statistics. So hang on. Averages, that's better. Percents, graphs, etc. So that's the first part of the class. We just call it descriptive statistics. Okay, it doesn't take long to get through descriptive statistics. We'll be done with that next week. And a lot of it you already know. So any questions? And then inferential statistics is really what I was talking about before. This is using statistical data, that is data from samples, to generalize, or as we say, infer, to large just to large populations. Any questions? Okay, so most of statistical inference is done by, in statistical inference, you're always trying to show that something's unusually good or unusually bad. Generally speaking, when things aren't unusual, there's nothing to report. When we put COVID, when we put people on a placebo to protect them from COVID, it's not unusual when 10% of them get COVID. There's nothing to report from a placebo when people start getting sick. Okay, that's not unusual. But then you have, so that's what's called a control group, a bunch of people that receive a placebo, meaning they're getting an injection of saline. There's no medication in it. Okay. The other group that you're studying is a treatment group, and they are getting an injection of one of the immunization medications that are out there. And if they get 10% infection rate as well, then you go, oh, that's just like a placebo. There's nothing unusual here. Okay. Those data values look just like the other data values. Now, when I say these values look like those, I'm thinking about how the values are distributed. So this is where I'm referring to what we call distributional thinking. that we've got this collection of values. We know kind of how they lie on like on a number line, literally. And now that we know what the normal values look like, when one of them comes in that's really different, we mean that it stands out and away from the rest of the data values. And that's sort of the key idea in statistics. We make decisions that treatments work well when they stand out from the group, which was people that receive a placebo. Okay. The new information that comes in should act really different or should look different from the distribution of all the other values, and those would be the placebo ones. Okay. So you have to have a sense of what the normal distribution of values is or what it looks like before you can decide when values are unusual or special, or they indicate that something's working really well or possibly something's working really badly. Okay, any questions about that? That's what this heading here is called distributional thinking, and that's what I mean. So distributional thinking, I would say this is knowing how a collection of data values lie on a number line so that we can spot unusual values. Those are the ones that are unusually high and unusually low. And in statistics, it's all about, the whole class really eventually is about determining statistical significance. And statistically significant, in a really kind of a rough way, you can define statistical significance is that any value is significant if it sort of lies apart from the distribution of normal values. Okay. And so you have to even have in your mind a picture of, well, what's a normal distribution of values? And so that's where the graphs come into play. And so the very first graph we're going to do here is a dot plot. Okay, and you can see I just have heights of adult women here. And we're just going to basically put these on the number line, but when values repeat, we pile them up in mounds. So the more frequent values look taller. Okay. So let's just zip through this. There's a 159, so I'll put a mark there. Notice I'm putting these above the line. So I'm just going to do this quietly till I see a repeated value, and then I'll say something then. So there's two 160s here, so I've piled those. Two 158s and so on. Oh, I think I made a mistake. Okay, so there's my graph. I'm just gonna let you guys catch up real quick here. Okay, so you can see how I can see right off the bat what unusual means here. I couldn't see that before. I can see that the unusual values, you know, this one up here might be unusual. Unusual is sort of another word for statistically significant. Okay.
Is Professor, is that also the outlier?
Yeah, it might be an outlier too, but I'm not going to call it that right now because there's a technical definition for that. Okay, it does it does stand apart, and I think that you'll see that there are actually 3 outliers here. All 3 of these turn out to be outliers, but I don't want to go there until I've defined exactly what it means. Turns out this really low one down here, the 148, is not an outlier, but there's a measure for that. So we're going to leave that alone. I'm just kind of saying, you know what, these values, clearly this 184 centimeter woman, she's super tall. Okay, and in a way that I would say is just really unusual. She's so far from everybody else that you think, okay, she's just really standing out and is unusual. She's special in that way? Of course, everybody's special, but she's super tall. Okay, and but we were able to do that when we know what the distribution of the data values looks like. If I'm just looking at these numbers, I can see she's tall, but I don't have a sense that it's really significant or how much she stands out without looking at the distribution. Okay, and seeing especially where the most common values are. I get a sense of the average here. So if you look at this on the next page, it says describe the center. Well, I would say the average is around, what do you guys think? And there's lots of different ways of computing an average. What do you guys want to say for the average height?
Maybe 159, since it's between 158 and 160.
So let's say 150, that's fine, 159 centimeters. And again, it's just a guess. So we know what the typical height is, the average height. We also know that people are pretty, compressed in here. If it says the shape, on the next part, we would call this a bell shape that is skewed to the right. I'll do a collection of little graphs somewhere on here so that you know what the different. Well, let's just do it now. I'm just going to do a pretty crummy collection of bell curves here. Okay, so if there's sort of a long tail on the right, this one's skew right. Okay, if that doesn't look very long. I'm trying to do better. It's not great. Okay, so that was skew right, and then skew left will have a little longer, sort of a tail on the left, like that. Okay, and of course there will be the symmetric case. Bell shapes are really common. Because with data, because it just kind of speaks to the fact that generally speaking, average values are sort of the most common ones. And so you see values that are close to average more than anything else. So this one's the symmetric case where you kind of have extreme values on both sides. So this one's symmetric. A true bell curve is a symmetric curve. And those are just some of the shapes. We'll talk more about distribution shapes because there's a list of them. Well, now for the spread, I almost want to kind of not include that outlier. When I talk about the spread, I might say most values go from 148 to 176. And then that unusual one is so not typical of the rest of the values. I think I'm going to leave it out. So this is just really informal. We'll have a measure of spread. So most values are between 148 and what I say 176 centimeters. That's a spread of 28 centimeters.
I have a question.
Mm-hmm.
How is the average around 159? How did you come up with that?
Well, okay, so first of all, we guessed, okay? And the average should be sort of in the center of most of the values. I realize some of you guys are gonna say, well, maybe the average should be over here. And then what I would say is, well, let's say this was a scale, okay? Let's say you were trying to balance this thing and those little dots that I drew actually weighed something, okay? Would this tip, if I tried to balance it where I've drawn the arrow, if that's not the balance point, then the best way to place an average is to find a balance point, a place where you can set this arrow where you think it'll balance out. So there was a guess that it was maybe 159. I might have said 160. I'm really trying to see how this will balance. But it's got to be in here somewhere where I'm moving this arrow, because I think it'll almost balance that. That's where I'd put my finger first if I was trying to balance it on my finger. Is that okay? Does that make sense?
Yeah.
Um,
Yeah, it makes sense. Yeah.
Yeah, there's different ways to average. One of them is to think of a balancing point, and that's called the mean. So when we do the formula for the mean, you just add the numbers up and you divide it by how many there are. And that'll give the balancing point. There's also a median. The median tries to get half the points below it and half the points above it. So if there's 30 points here, I don't know how many there are actually. It doesn't say. So if there's 30 points here, I'd want to pick a value where 15 are below and 15 are above. But as it stands right now, we just guessed. Okay. And if you don't like 159, use a different guess. But it should be not too different from that. 160 is fine. 161's fine. I think if you go up to 162, you're starting to push your luck. Okay. It's just a guess. And so then the last thing is, this whole notion of the unusual value. I didn't call it an outlier, but I did call it a possible outlier. And that's the woman who's 184 centimeters. So I'll just say maybe the 184 centimeter woman. Okay. Any questions?
So what if there are like two outstanding points on the plot line, would they be considered as unusual again?
Yeah. I think I mentioned. I think all three of these are outliers.
Okay.
You'll see that. Okay, we'll revisit these values next week, and we'll learn to classify outliers, and it's based on how many. Oh, it's a long story. You will have some measures about basically. You have this tape measure you lay out, and if they're more than 1.5 interquartile ranges from the third quartile, isn't that ridiculous? That's the rule. So I need to talk about what all that means, but there's a rule. Okay, and then for data types, we'll go ahead and just talk about this. So categorical data, these are just these are values that fall into categories, obviously, but they would be values that are non-numerical. I don't even want to say values because that sounds like a number. So let's just say observations. Let's say that are not quantities. Okay, and you guys all know what quantities are. So these are quantities for the quantitative data. Okay, so I'll throw some at you here. So color, maybe I should say colors. Categorical or quantitative?
Categorical.
All right, so we'll put colors here. How about nationality?
Categorical.
Quantitative?
Nationality, these are not quantities, they're not numbers, right? So these have to be categories. When you describe someone's nationality, you're putting them into a category. Okay. Maybe that's a good thing, maybe that's a bad thing, but it's still categorical. Okay. What about zip code that you live in?
Categorical.
Good. Zip code is a number, but it's not a quantity. Okay, how about height?
Quantitative.
Yeah, height goes under quantitative. Okay. How about the number of children in your family?
Quantitative.
If it's a number, it's quantitative. Something like that. You can say temperature or whatever. Okay, so and then there's a little bit of difference between discrete and continuous data. These are quantitative now, so these are definitely numbers or quantities. But we treat them differently when we do probability because it's really easy to get discrete values and it's really hard to get continuous values. They're both quantities, but continuous values, they sort of crowd together and make it really hard to get particular values. So with discrete quantitative data, these are quantities that you can list. Let me see, what's the best way to say this? I'm going to say quantities that you can count. Okay, and in parentheses, I will say there are gaps between consecutive values. Okay. And then with continuous quantitative data, these can't be counted, must be measured. Okay, and there are no consecutive values with continuous data. So you can't even say there are consecutive values. Okay, so if you say, well, if you could say it's 59.5 degrees outside, or you could say it's 59.6. That's not the next value. Between 59.5 and 59.6 is a 59.55. And between any two, you can average them to get another temperature that's just as legitimate. So there's no next value. If there was a next value, you'd be able to average those and get something in between them. So then it's not a next value. So that's the weird thing about continuous quantitative data, is that there's just no gaps between possible values, and that makes it really hard to list them. So they can't be counted, they must be measured. So let me just give you examples here. Can you count how tall?
No.
You count your height and measure it. It's a quantity, right? How tall you are. You count it or measure it.
Measure.
Right, so height is a continuous measurement. Oops. And heights get real close together. You can get people that are, 1 millimeter different in terms of heights, or less than a millimeter. So these measures get real close together. What about the amount of money in your pocket?
We count it.
You
Discrete.
can count.
Discrete quantitative data for that one.
Yeah, so money in your pocket, you can count. It's not a whole number. You'd say 1.03, that's $1.03. Okay, money in your pocket. Money has to be a discrete thing so that we can count it. We like counting money. Temperatures?
Continuous variable. I'm sorry.
Temperature. That's good. That's
Data.
fine. Yeah, they are a variable. So how about your zip code?
Discrete.
Wait a minute, is a zip code quantitative?
No, that's the categorical.
Yeah, so that was a trick question. Discrete doesn't go into either category because it's not zip codes don't go into either category because they are not quantitative. Is that right?
Yeah.
Okay, but you could put number of children. As discrete, so because hopefully if you live in a family with lots of children, hopefully you can count them. So that's discrete. Okay, heights, temperatures, weight, all these other things that you use measuring devices on, like a ruler or a scale or whatever, those are going to be continuous. Any questions? Okay, so those are important distinctions. We'll have two types of probability distributions in this class. First, we'll learn about discrete probability distributions, and then we'll learn about continuous probability distributions. And the math behind them is completely different. With discrete distributions, you just need algebra to do probability. And with continuous distributions of probability, you need calculus or technology that does the calculus for you to do probabilities. So we'll do continuous probabilities, but we'll use technology for that. Remember that bell curve that I showed you on Desmos, the graphing calculator? That's how we'll do probabilities. I don't think I have that open anymore, but we'll do probabilities using Desmos for discrete variables or discrete data, I guess I could say. Okay, any questions? We'll take a break as soon as we get through these 4 examples here. Okay, so the last thing is levels of measurement, and they are nominal, ordinal, interval, or ratio here. These are 4 basically, it's just like it's just another way of sort of talking about the least refined type of data and the most refined type of data. And the refinement level is what they're calling the level of measurement here. Okay, nominal, ordinal, interval, or ratio. And so if you go across these rows, the nominal level, nothing works for it. It's the worst kind of data. Meaningful ordering, you might add to this that alphabetical ordering isn't meaningful. I can hear a phone, I'm sorry. So when someone says, hey, a list of names, does that have meaningful ordering? Well, you can order them, but it doesn't mean a thing when you put names in alphabetical order. It's just sort of somebody randomly picked the order for the alphabet, and now that's the order, but it was random, and random doesn't mean a thing, okay? Meaningful differences where you can subtract 2 measurements and get a meaningful result. Okay, so I will say meaningful result through subtraction. Okay. Meaningful ratios and zeros sort of make it clear what that is. There are some scales of measure where there is a 0, but it doesn't mean anything. It's again just a random placement of a number on a number line, where 0, essentially meaningful 0 is where 0 means none. Oops. Okay. And the thing about meaningful zeros is that if you don't have a meaningful 0, then you can't do ratios, meaning you can't say that 10 is twice as big as 5 if 0 doesn't mean none. So I'll talk, this will be clear in an example in a minute. So again, nominal, you're saying no to all of these. Ordinal has meaningful ordering only. Ordinal, sorry, I just said that. Interval, you can order and subtract meaningfully. And then ratio, you can order, subtract, and there's a 0 that means none. Okay. So here come the examples. So how about names? By the way, nominal, the root is nom, just like nombre, which is name. So if I was to say names, like your list of names, you can put those in alphabetic ordering, but it's not meaningful. So you can't meaningfully order names. You can't subtract names. And there's no 0 names, so names are nominal. Okay, does that make sense? And of course, nominal means names. Okay. How about
Question for nominal. Did you mean to put nominal again, or did you mean to write names?
no, I didn't mean to do that.
Thank you. Sorry.
Yeah. Oh, well. Thank you so much. And then how about, let's do rainfall amount in inches. I'll just say inches of rain.
Interval?
Can you sort you like interval? What about ratio for inches of rain? Is there a meaningful zero there?
Yes.
Okay, I found this on the web for Is There a Meaning Phys Ed row there. Check it out.
So that was Siri. Go away. It's kind of cute. What did we say? Was there a meaningful zero for rainfall amount?
Yes, I believe.
Yeah, you can have 0 inches of rain if it doesn't rain, right? So I would say inches of rain. Makes sense to me that you could have 0 on that one. And you could certainly sort, if you have a whole bunch of rainstorms, you could sort them from, lowest to highest. That's meaningful, the least amount of rain to the most amount of rain. You can subtract them and say, okay, we had 10 inches in this storm and 5 inches in that storm, and the difference is 5 inches. So that storm produced 5 inches more rain. All that makes sense. Okay, so that's good. How about months of the calendar year? The actual month names. Now they are names. They are names, so you get that nombre idea. But what else?
Interval?
Now, can you subtract months?
Oh, okay. Ordinal.
So,
Nominal?
yeah, there's definitely an order, right? So this would be month or maybe days of the week, right? But maybe like there's a good, better, best rating, which you sometimes see, or maybe more likely letter grades in class. So these would all be things that sort of have natural orders, but 0 does not, sorry, but you can't subtract them because they're not numbers. Okay. We would put, if we could put nationalities here up in nominal.
Couldn't you subtract some months from like let's say like, oh, I don't even know how to ask this question. Never mind.
Yeah. So I would say maybe like if you're talking about month numbers, but it doesn't really mean anything clear because months have different numbers of days. So if you were to subtract month numbers, that wouldn't be a specific number of days because it would depend on whether February, which is the shortest month. Does that make sense?
No.
Okay, so if you take March and subtract February, what do you get?
I guess 3 days or 2 days. I don't know how many days March has.
Oh, you're taking the number of days. I didn't ask you to subtract the days. I asked you to subtract the months.
So 0.
March minus February? March was you're still subtracting the days, but March has more days than if you're going to do that, March has more days than February.
Yeah.
Okay, can we just agree that this is not a well-defined subtraction?
Yeah.
So I want to say if you were to start subtracting months, people would go, what? And just because you might come up with some scheme for subtracting months, but you'd probably have people rolling their eyes at you. So, because it's just not clear what it means. Same thing, if you're going to start subtracting letter grades, I guess you could say that an A minus a B is 1, meaning they're one letter grade apart. But it doesn't really mean anything because an A could be 99%, but it could also be 91%. So what's that mean if you subtract a B? I mean, that B is a range of values also. So I don't want to start talking about subtracting words like month names or letters like letter grades. So that's all, because none of it's clear as to what it means.
Yeah, it makes sense to me now. Thank
Okay,
you.
Yeah. Now,
Well,
what about
I have a comment about that real quick.
your comment? Let's hear it.
Well, if you're talking about like history, prehistory, cultural anthropology, and you're dealing with calendars, Gregorian versus Julian, or Mayan versus Aztec, and you're trying to figure out times and dates of rulers or peoples or villages, then it would come into play, and it would have a significant meaning. But I think that would probably be.
Would you treat numbers as, would you treat month names as numbers?
Well, not the names, more just the numbers as a quantitative measure, and then trying to figure out which months correlate to specific periods or differences between periods, to get to what would be equivalent to October versus July, or
You guys are too smart for me. You're thinking way harder than I'm thinking. So yeah, I think all of these, even with, like, if I put colors under nominal, people will say no. People say no, it's ordinal, because colors have an order, right? It's the whole red, orange, yellow, green, blue, purple, right? That's the color of the rainbow, and that's from low frequency to high frequency of the light wave. And then I would come back and say, oh yeah, well, what about taupe? Where does taupe go in that list? You see what I'm saying? So you might be able to make an argument that you can order colors on a number line. I think colors are more two-dimensional, or maybe even three-dimensional. So because when you blend colors together, you're mixing, there's three primary colors, right? Plus there's the tint, and all that other stuff. So I put colors up there, even though some people would argue with me. And that's fine. And I don't know that there are absolutely right answers to some of these questions. How about the calendar year? So this is 2021, right? So when I say calendar year, I mean 2021, or when I was born so long ago, 1963.
That one's
It-
interval?
I could definitely subtract, right? And if you took your birth year and subtracted it from my birth year, that would tell that I'm, 20, 30 years older than you, right? So, or more. And that's a meaningful measurement. So subtractions make sense. Is there no zero? You're telling me that there's no zero calendar year?
depends on the culture.
Okay, I'm talking
So it's
about in
ratio.
our culture. Is there a zero? always thinking so hard. On our calendar, in
So it
whoever
would
uses the
it would be ratio, because if there's a zero, that means you're the same age and it has a meaning.
but does zero mean none? So there is a zero calendar year, and it was 2,121 years ago. Okay. And the world did not begin on that day. The universe did not begin on that day. Nothing in particular began on that day. Yet there's a 0 year. So, but it doesn't mean none. You guys follow me on this? Now you could probably come up with some way to make it so that 0 means none. There's always a clever way to do that. Like you could say, well, the calendar year just measures the number of years since year 0. And now I've just made it a ratio measurement, because 0 would mean no years since 0. Do you hear what I did? So you could pull it off, but that's not what people mean usually when they talk about the calendar year. So You guys are going to give me a hard time on the exam because I'm going to be marking you wrong. You're going to be going, yeah, well, what about this? And then you'll bring up the Mayan calendar and I'll go, okay, fine, you get it right. You get it right. Calendar year temperatures are the same. I'll go ahead and list degrees Fahrenheit or degrees Celsius. Does anybody want to say, well, what about on temperatures? Come on. I'm expecting it because there is a what about on temperatures.
So yeah, doesn't the zero you said means none? Does that for temperatures 0, doesn't that mean something? So
I mean, does it mean no heat? I mean, you're measuring heat, so it should mean no heat. Do you agree that it means no heat?
okay.
I guess I should ask, does it get colder than 0?
Yes.
Because if it can get colder, then there's still heat that you're subtracting. So
Are we talking about
0,
kelvins?
there's the what about. So let's put temperature in Kelvin down below.
Oh my God.
So Kelvin scale was invented to fix the problem with Fahrenheit and Celsius. And what's the problem with Fahrenheit and Celsius? The problem is 0 doesn't mean none. So you can't do ratios. You can't say that 20 is twice as hot as 10 if you're measuring in Fahrenheit, because it's not. It would be like saying think about this, you guys. In the year 2, was the world twice as old as in the year 1? I mean, whether you believe in, evolution, where the world is billions of years old, or whether you don't believe in that, the world was still really old in the year 0. So in the year 1 and the year 2, the world had not doubled its age between year 1 and year 2, even though the number is twice as big. So that's going back to this notion that if 0 doesn't mean none, then ratios don't mean anything. You can't say, oh, it's twice as big if 0 doesn't mean 0. Okay, does that make sense? But you can in Fahrenheit, in temperatures in Kelvin, 0 kelvins, there's absolutely no heat left. You've completely removed all molecular energy at 0 kelvins, and it's possible to do that. There it goes again. I got to turn that on. Okay, any questions?
I have a what about. For interval, could we also say like each letter grade, because there are also intervals, right?
Yeah, but they're not. When we measure intervals, they have to be numerical. So you're subtracting numbers to interval. So I would say, if you want me to subtract grades, let me do it with the percentages. So I could get your overall percentages and then say, okay, this person got 10% higher than that person. Now, if you're subtracting letter grades, you might say something like, well, this person got 1 letter grade higher than that person, but I still don't want to talk about subtracting letters. Okay.
So it's not basically subtraction. So we could say just like B is between 80 and 90, and A is between 90 and 100.
Yeah, but now you're dealing with numbers, and it's okay to subtract. Once you actually start talking about numbers, then it's no problem subtracting them. So we don't want anything that's not a number to be able to be called interval. Interval data has to be numerical, and
Okay.
both interval and ratio have to be numerical. Otherwise, you can't take an average of letters. Okay, and all of that's really important in statistics. Okay, and then again, probably some of you are like, well, I bet I could, but that's because this is the honors class. All right, let's take our break till 10:20. If you guys have questions to ask, save them up, and we'll talk more at the break. at the end of the break. So I'll see you soon. Okay, I'm back. I just been scrambling trying to figure out what happened to the homework, and little bit of trouble pasting it over because it's just not working right. So if you let me go ahead and share this on the syllabus. Okay, so basically, same syllabus we were talking about before. I'll get this straight this week. What I've done was I was able to paste in the homework for chapter 1. And you can see I put, there's only one problem in 1.3, and that's extra credit. So I'll just add another point to your homework if you want to do that. It's a fair amount of reading to do that. So, but one point on homework adds 10% to your score. So if you want 10% more on your homework, then be my guest. They do accumulate. There will be homework scattered about through the class. Or sorry, extra credit scattered about through the class. So if you like to accumulate extra credit, it does accumulate nicely. So it's up to you. Okay. It helps especially for people that are borderline grade wise. So these, you can see 1.1's got a fair amount of problems for you guys to look at. There's almost 20 problems there. So that'll take a little bit of time, and they're not too hard. It's just going over the definitions we just covered so far this morning. Okay, any questions about the homework? You can just count on this as being your homework for this week. Okay.
So, Professor, on those, when I was looking at the book, are you talking about the exercise numbers, the exercise, or the
Exercise. No. These are just the exercises in each of the sections. So at the end
Okay.
of section 1.1, you've got exercises and so on. Okay.
When is this due by?
I'm collecting homework at the midterms, so you won't have to turn this in until test 1 is on the 26th of March. Okay, so I recommend you keep up, and I'll be taking homework questions at the beginning of each class. Okay, anybody else? All right, and I'll have more homework questions posted on there, but right now I'm having formatting issues basically. Let me go ahead and jump back to the material. Okay. So I think we can go ahead and jump into 1.2. I think you saw that 1.3 will be skipped. It's extra credit. So you can do what you like with that. We're just going to go ahead and kind of emphasize section 1.2 is just basically problems to look out for. I called it where statistics fail. Okay, and so the basic idea is we recognize that all statistics have error when we use them to estimate things that are bigger, right? When we generalize from small samples to large populations, we get errors. So error is just it's really a statistic minus the parameter that we're estimating. Okay. Oops. Okay, so and let's see, I got absolute value bars there. A statistic is an estimate. This is the true unknown value, the parameter. That we're estimating. Okay, and this error almost always exists in statistics. And that's a really important takeaway from this class. Next we go to the night. Okay, that's covered. Okay, good. Okay, now when we talk about error, we're going to be breaking it down into sources of error in statistics because it's always nice to know where error comes from. So we have sampling error and non-sampling error as the primary sources. So sampling error is when we use subsets of populations which we've called samples. To generalize about entire populations or about the entire population. Okay, just the very fact that you're not using the entire population will cause sampling error. Okay, this causes error. Okay, I'm gonna make this fit a little bit better. Now you can't help this error. If you're working with samples and you have no choice but to work with samples. And if you're going to work with samples, you're going to have error. So that's called sampling error. Is there any question about that? Okay. The non-sampling error, this is due to sources beyond sampling. Okay. So this is due to any source, any other source than just sampling. Okay. So a non-sampling error can be bias that skews results. And if you want a term if you want to define bias, you can see I'm going to define it down below. But basically, bias is when there's something wrong with your procedures that tend to make your answers come out too low or too high, or your estimates tend to come out too low or too high. So bias can be how you pick your sample. Bias can be the way you ask questions in your surveys. Can bias the information. Bias can be, there's just lots of types of bias. So we'll address that in just a second. So bias that skews results is one. Arithmetic mistakes is a way to bring non-sampling errors. Okay, etc. So bias occurs when there's a tendency for results to be either too small or too large because of a systematic flaw in the design or maybe implementation of a study. Okay, so this is when statistics tend to be either too large or too small due to flawed implementation or design. Of a study. Okay, so you're getting numbers that are just either typically too high or too low because, and it's your fault. It's because you are not doing it right. Okay, that's different from the sampling error. Bias brings non-sampling error. Those are the ones that you want to try to avoid. You can't avoid sampling error. You want to make it as small as possible, but you can't avoid it. Okay, so there are 3 types of bias. That we will address. You can probably come up with any number of biases, and it sort of depends on how people define them. But let's just go ahead and real quickly talk about these. Selection bias is when some population members are more likely to be selected for the sample. Than other members. And that's really hard because if you think about it, I mean, some people are just really hard to select. And and it's getting harder and harder, I think, with people that just naturally, if you're trying to call people on a phone, people hang up. So that makes it hard. And if you email them, it goes straight to the junk folder, right? And so, and there are large reputable organizations out there that still gather information by calling people. And I think that it's been a huge challenge in the last 10 or 20 years, and it's getting worse all the time when polling companies, especially as the elections get closer and they're doing polling all constantly, and calling people, and thousands of people are being called. And when 75% of them just hang up the phone. And so that's going to really introduce bias, and it becomes a challenge for them to figure out ways to get around it, to somehow minimize the bias. The result is bad predictions. So if you've heard stories about, it's really hard to know how many Republicans are going to vote for Trump in the last election if Republicans that are going to vote for Trump are more likely to hang up the phone. I don't know that that's true, but what I do know is that there's been a huge problem with undercounting Republican votes. And that may just be because there's a tendency right now in the Republican Party to not trust the establishments of our country. And so if you don't trust polling, or if you don't trust the news, or you don't trust any research that goes on, then you're probably less likely to join. And that term, less likely, just means selection bias. Okay, remember, selection bias, everybody has to have the same chance of being selected. And if you're not getting enough Republicans just because they fundamentally mistrust the systems that we have in our country, then you're going to get bad statistics. And we've seen it repeatedly over the last few election cycles. And, hopefully at some point we'll all start coming back together again and rediscovering faith in our institutions. And then all of a sudden, things like this become easier. Any questions or comments? I think the fundamental issue with the flaws of polling organizations right now is just this issue where some groups are more likely to hang up when they're called than others. And and you're going to undercount them. And boy, that just makes it hard. Okay, let's do the next ones. I can't talk so much on all of these, but response bias or measurement bias, these are really the same thing. So this is when the method of gathering info interferes with the data. Oops. Gosh, I can't spell. So I'm going to say interferes with the measurements or responses. And we'll do examples of this in a second, but it's pretty easy to ask questions in a way that are what we might call a loaded question, where you're sort of trapping people into saying something you want them to say. You're not really interested in their opinion. You're just trying to get them to say something. So that's kind of a loaded question. There's just lots of ways to ask questions that influence people's responses. And it's actually hard not to do that. So when you do that, that's called a response bias or a measurement bias. People are responding incorrectly. And then a measurement bias would just be like if your measuring device, this is the same thing. You're gathering data, but you're changing it somehow as you gather it. If it's a measuring device and the measuring device is somehow doing it wrong, that's the same thing. So a measuring device has to be calibrated so that if nobody's standing on the scale, that it should measure 0. That's a hopefully properly calibrated scale. If it's not calibrated, then there's going to be a tendency for the numbers to either be too high or too low. That's bias. Okay, so if the scale says 10 before you get on it, then there's going to be a tendency for all the numbers to be too high. Again, that's bias. Any questions? And then non-response bias is pretty easy. This is just when many participants, let's say sample participants, refuse to answer questions. And the idea is, boy, if you're refusing to answer questions, there might be a reason, and that reason might be really important. And people like you are not going to be counted in my survey. And you might have really strong opinions, but you're keeping them to yourself. And I'm not going to be able to measure that if you won't tell me what's going on in your head, and that's going to bias the data. So that's non-response. So you've already been selected. You've been selected maybe without bias, but now you will not talk. Maybe it's just one of the questions that I've answered or that I've asked you. There's just one where you're just not going to answer. That happens a lot. Okay. So let's go through these examples here. Any questions? Okay, so the first picture is something we'll see a few times this semester. We have this beautiful bell-shaped distribution of the first 100 measures of the speed of light that were measured here in Southern California. They had a cool contraption where they were shining a light, I believe, from Mount Baldy to a mirror on Mount Wilson, reflected back to Mount Baldy, to another contraption, which is just crazy when you think about reflecting to a mirror on a mountain that's tens of, dozens probably of miles away, and then trying to get that mirror straight enough so that the beam bounces right back to where it started. And then they had a really amazing contraption for measuring how long it took to cover that distance. And this was back in the early 1900s. So it was just an amazing feat to measure the speed of light that way. But this is a distribution of values, the 100 estimates of the speed of light. But the true speed of light is right here. Okay, now, again, these were early days. And when I say the true speed of light, that's our current understanding of how fast light travels. So you can see there's a tendency here for the estimates to be either too high or too low. Tendency for the estimates, the actual data that were gathered, to be too high or too low.
Too high.
Some of them are too low, but most of them are too high. So with most of these being too high, that's a tendency to be too high. That's just bias. So the question is, what type of bias is it? Is it the way they were selecting data? No, they were just measuring data. They were just measuring speeds of light. So was it the way they were selecting data? Was it the way they were measuring the data with response or measurement bias? Or was it because the data was refusing to respond?
A measurement bias?
As their measuring device was just, it wasn't working that great. It was pretty good, but it wasn't perfect. So this is going to be measurement bias. The measuring device itself is skewing the data. Oops, sorry, measurement bias. Any questions about that? The device is affecting, if they're all coming out high, most of them are coming out high, then it's the device that's doing that. Okay, any questions? All right, so the next one says data were gathered by a news organization by asking viewers to log onto a website to take a survey. Will bias be a problem with these data? So think about the three biases. Will there be selection bias where some people are more likely to be doing it than others?
Yes.
Is that the one?
Mhm.
So
Because a lot of them, if you're doing it online, most of them will just skip over it.
right, and so you get these people that are just bored, right, or maybe super cheerful and they love to do stuff like this. Not too busy people to do stuff like this. So if some people are more likely, then that's just the definition of selection bias. Okay, and let's just go ahead and say some people. Oops. Will be more likely to participate. For sure.
Since it's a survey, could we say also non-response bias?
Not unless we know that they didn't respond. So the problem is there's no information about them not responding. So let's not guess about what the problem might have asked. You see what I'm saying?
Yeah.
I realize there could be non-response bias, but it's not evident. You need to have some, if you're doing this on an exam or whatever, you need to be able to look at what the question asks and not add to it. Okay, so by me saying, oh, some people won't respond, I would come back and say, well, where does it say that? So, okay. The clear bias here will be the fact that people are, you're not going to them, you're asking them to come to you, log onto a website, and that's just going to be problematic. Okay. Let's go on to question 3. I love this one. So this goes back to the kids carrying guns on campus. So researchers surveyed 1,000 randomly selected high school students, asked them if they've ever, and by the way, if they're randomly selected, and random selection just means everybody has the same chance of being selected. That's the definition of random. Okay, randomly selected California high school students, asking them if they've ever carried a gun on campus, what type of bias will most likely affect these data?
No non-response bias.
Yeah, this one you're gonna be non-response. Now it doesn't say that either, but it says most likely now. I would think students that have carried a gun will probably not say they have. Okay, so they will.
Wouldn't
need a lot.
response, oh sorry, wouldn't response bias also fit there, since you're personally asking them to their face and they might lie and say yes or say no just because you're in person and it's not anonymous?
Yeah, I would have to give you credit for that answer, for sure. I'm not going to argue with that one. Just the fact, what you're saying is I could do this in a way that would maybe preserve their privacy, and so if it's my method that's influencing how they answer, then that's my bad. And so I would call that a response bias. Yeah. But I want to go ahead and say that the most obvious one is students aren't, I don't know which one's most obvious. Some students will not answer. I'd say, especially if they've carried a gun. This is the answer I intended to give for this one. And then you can imagine that response bias is probably an issue here. Okay, any questions?
Yeah, so I'm just wondering, so if we were asked similar questions like on the exam, would you want us to explain why or just write the answer?
I'll usually tell you to explain. I'm going to always, generally speaking, I'll always explain here because these are notes and I want you guys to feel why did he say yes. But generally, I'll ask you to explain stuff on an exam if I want you to explain. Okay, on question 4, it says in a survey, researchers asked the question as follows: only 3% of landfill is composed of disposable diapers. Is it fair to tax disposable diapers to help pay for the disposal? Could that, the way that was asked, could that introduce bias?
Yes.
Why?
Well, you're giving them a stat already. You're giving them some kind of information. So the way you're
telling them why it's not fair, aren't you?
yeah, with that just only 3%. Like, how do I know if it's only 3%? If that's the case, well then yeah.
Okay, good. So what kind of bias is that?
Measurement?
Yeah, and in this case, measurement, I would call it a response bias because there's a clear human response here. But measurement bias would be good for full credit also. So, but here I'm going to say it's response bias, which is really the same thing. The question is suggesting it's not fair. Okay, I'm going to say the question is suggesting a particular answer. Now, it might be good to know that it's only 3%, but you should give balanced information. So I'm going to say it this way. If information is given, let's say it this way, it should not be one-sided. So the way you might fix the question is just take the only 3% out. Okay, or if you feel like you need to give information, you'd say it's only 3%, but it's still 100 million tons a year. You follow me? And if someone says, oh God, that's a lot of diapers, maybe we could talk about that. But I think the 3% number is important, but it's not balanced. Okay, any questions? Okay, let's go on. We've got some more terms here. Variables. This is any observations. Can change from individual to individual. I didn't want to say can vary, but that's what I mean. And I'm not saying person to person because I don't know that these are people. They could be rocks as far as I know. Okay. So that's easy enough. The harder term is explanatory and response variable. So an explanatory variable you think might be related to another variable, okay, or might help explain. That's why we say explanatory. So this is a variable that might explain the behavior of another variable. Okay, so let me give you an example. Cities with more guns have higher violence. I'm going to say higher murder rates. So cities with more guns have higher murder rates. Okay. So the number of guns is the first variable. This is the explanatory variable. Okay. You think the number of guns might explain the murder rate? Okay, any questions? And explanatory just means it's used for making predictions. Like, can I predict the murder rate? Okay. Okay, and then the murder rate would be the response variable. So the response variable is a variable we can predict if we know the value. Let's say somewhat reliably predict. Okay, so this is the variable we can, well, let's say we hope, that'd be better. We hope to predict based on the value of an explanatory variable. Okay, and then in parentheses, I want to add this. This may not be cause and effect. Okay. Some variables have relationships between them, but one is not causing the other. So I know, as as you age, you get more cavities in your teeth, but it's not really your age that causes the cavities. The variables do relate. I could predict with some reliability that you have more cavities when you're older. So there's a predictive nature there. But I'm not going to say it's because that the age is the cause, because we know that there are some older people that don't have any cavities at all. So it's not really a cause and effect thing, but there's a relationship. Okay. And same with the cities and guns. We know that cities with more guns have higher murder rates, but I don't know for sure, and nobody's ever going to know for sure. And we'll talk about this later. No one's going to know for sure that it's the higher number of guns that causes the higher murder rate. Because I always like to turn that one around and say maybe it's the higher murder rate that causes people to go buy more guns. And the fact is, I don't know which one's causing which, and it may be neither. There may be just a third variable, like how much violence is in a city. Maybe that causes people to buy more guns, or how much racial strife is in a city. That might cause people to buy more guns. I don't know what the cause is. What's the root cause that drives all these things along? And these are super complicated issues. So it's a waste of time for us to try to explain them, especially when we can't really do a real experiment on this. You can't do a statistical experiment on how many guns are in a city, on whether more guns cause more violence, because you have to do a controlled study on this, and nobody's going to do a controlled study on people shooting other people. So, okay, with guns. Okay, so correlation between two variables. This is when let's say the value of one variable of, let's say, an explanatory variable can be used to somewhat reliably. Doesn't have to be perfect. It's better than a random guess. Is that what that means? Predict the value of a response variable. And again, in parentheses, not cause and effect. Okay. But you see the word causal relationship there. So this is where there is a cause and effect relationship. And we do experiments for cause and effect. And we'll talk about experiments shortly. But you have to be really careful and a different type of statistical study to determine or to infer cause and effect. We don't really determine things, but we provide evidence in statistics. So there's no such thing as proof, but we can infer by providing evidence. Okay, so causal relationship is when the value of one variable, let's say an explanatory variable, is the cause of the value of a response variable. So I'll just add, let me mute that real quick. Oh, looks like we got it. Okay, so I would say that the number of guns in a city and the murder rate in that city are correlated but not causal. And we'll talk more about exactly why it's not causal, just so that you know how to answer the question. Can we prove cause and effect in this relationship? You can't. And again, because it's not no experimental study has ever been done on this. And the simplest meaning of that is you have to give a bunch of people guns randomly to do an experimental study on gun violence. And nobody's going to randomly hand out guns to people and see if they go out and see how many of them kill people. It just will never be done. And because nobody can ever do a real study on this, you can't do cause and effect. Okay. But you might say the relationship between getting an approved COVID-19 vaccine and not dying from COVID-19 is one of cause and effect. This is inferred in a controlled experiment. Let's say by the controlled experiments done by researchers. And you've heard enough, I think, in the last year to know that all the companies that were monitored by the FDA, that our Food and Drug Administration, had to do a controlled experiment that involved a bunch of people getting the vaccine and then a lot of other people getting a placebo, and the groups were randomly assigned. There's a whole list of things that has to be done to show cause and effect. It's not just randomly selecting people, it's randomly assigning them to groups where one group gets vaccine, the other group gets a placebo. And the groups should, because of the randomness involved, the groups tend to be pretty similar, especially when there's 30,000 people, which I think is what a lot of these studies have had. So you divide them randomly, you have groups that are really similar. One group's just getting sick more. And again, none of this is proof, but it's strong evidence for a cause and effect relationship. Okay, any questions?
So like when they say this vaccine is like 90% effective, is that like something that relates to this?
Yeah, but that's a little more complicated. I mean, they're comparing how effective it is to the placebo. Okay, so basically, you need 95% fewer infections in the group that's getting the vaccine. And if you have that drop in infections, then you can say it has a 95% effective rate. Any questions? Okay, you're just counting how, you're comparing the rates of infection. And you see some people that get the vaccine still get infected, but those who didn't, we could say it is because of the vaccine. Okay. Anyway, and nothing's 100%, but we're still using cause and effect language. Okay, so the last section for today, we've got half an hour, so I'm going to see if we can get through it. It's section 1.4, and it's on types of statistical studies. So the first type of study is an observational study where we use a representative sample to generalize about large populations. And unfortunately, this statement down below, what are the conclusions look like? These are generalizing. I'm restating the sentence I just wrote, so sorry about this, but these conclusions are generalizing about large populations. Period, but I would say only reliable when the samples are representative. So it's a little redundant. Okay, so it's super important though. So super simple too. That's it for an observational study. I don't have to go into a lot of depth here. Representative samples are hard to do because it's hard to get representative observational studies are hard. Sorry, I'm going to try this again. Observational studies are only hard because it's hard to get representative samples. The experimental studies are a little different. This is where we divide individuals. Okay, I can't spell it. Into groups apply different treatments to each group. And I said into groups, let's say similar groups just to nail that down. Okay, it's into similar groups, apply different treatments to each group to observe the different responses. Okay, I use the word response. There's a response variable. And what's the other variable? The explanatory variable is the treatment. The response variable is just how people respond to the treatment. Okay. Conclusions in experimental study, we can conclude cause and effect to the treatments. if the groups are similar. And the reason for that is that you eliminate alternate explanations. Okay, we want to know exactly why people get better when you put them on a treatment. So if you put one group on a treatment and another group on a placebo, if the groups aren't the same, then there's all kinds of reasons why one group might do better. But if the groups are similar, so you take these 30,000 people and you divide them randomly, you're not going to get all the women in one group, right? And you're not going to get all the old people in one group. It's random. So the groups just tend to randomly be kind of similar. And if it's a large number of people, there's no way that they're going to be, very different in terms of age or ethnicity or anything. You're just it's random. Okay. So if you divide randomly, you're going to get similar groups. And then when one group does better, then the only explanation is the only real difference between the groups. And that is that one group got a treatment and the other got a placebo. So that's the idea. But we're going to talk about observational studies a little bit before we go into depth on experiments. So for observational studies, as we mentioned, you want to gather a representative sample and make a conclusion about a population. All right, so that's pretty straightforward and nothing to write there. So random selection is how we gather, and I guess it says representative sample, and here I'm going to say through random selection. Some sort of random selection. Okay. Random selection just means where we pick in a way where all individuals, let's say all population members, have the same chance of being selected. So that eliminates selection bias. If they don't all have the same chance of being selected, then it's really hard to generalize to the population because you're just going to have a weird non-representative sample of just certain types of individuals. Okay. So the question is, how do we come up with a random sample? There's 5 different methods of getting a representative sample. So random sampling is where we choose members through random selection. That's pretty straightforward. Okay. That usually, this works well. Okay, it just works well when possible. So, I can randomly pick names of Mount SAC students if I have access to the database. And that's a really great way of getting a random sample of Mount SAC students. There's a list. I can pick from it, no problem. But when there's no list, now it gets harder. There's no single list that has the name of every American on it. There's lots of people that are excluded from the list. And because of that, it's just going to be really hard to contact them. Okay, stratified sampling. This is really great. This divides the population into groups, into logical groups. You can think about like political groups, like political parties, or you can talk about gender, or you can talk about race, you can talk about ethnicity, you can talk about all these just sort of natural groups, things that we sort of divide ourselves into all the time. And then just make sure you pick people from each group. So into logical groups, then randomly selects members from each group. That sounds like a great idea to me, and most polling organizations use this. You get people hanging up on you constantly. Because I can't talk them right. Organizations use this. And if you think about what I had said before, you know, if Republicans have lost faith in American institutions, then they're not going to participate in your poll, very likely. Some of them will, okay, but they're just less likely. And so if you've gone out and talked to 1,000 people, maybe without any bias, intentionally, you ended up with 800 Democrats and only 200 Republicans. So the idea is, okay, so I've got Democrats covered. Let's look at these two groups, these natural groups in the population, and you better go out and get a bunch more random Republicans. So you're making sure you have 800 Republicans and 800 Democrats, and it may take you a lot more work to get the 800 Republicans. But if you preserve your randomness and you just select from that group, now you're doing stratified sampling. Is there any question about that? Okay, then so I'm going to underline or highlight the word each here because it's a little different in the next one. Here with cluster sampling, we're going to divide the population into groups. These are clusters. Then randomly select from randomly select some groups to survey. So there's still a randomness to this. I'll just say for the sample. But you're not selecting members from all groups. This can work, but it's a little more problematic because you're going to leave some groups out for sure. And the key difference here is with stratified, you're going to each group. With cluster, you're randomly selecting some groups, not all of them. Okay, you guys see the difference? So if I want to study English students at Mount SAC, then the natural groups are just the classes, each class of English students. And if I randomly select 100, they probably have 100 sections. So let's say I randomly select 20 sections to get students from. That's a cluster sample because I'm not going to all the classes. So the groups are the classes. If I go to each class, it's a stratified sample. If I just randomly go to some classes, it's a cluster sample. See the difference? Systematic sampling is where we line up population members that could be on a list. Doesn't have to be a list. It could be like an assembly line in a factory. Okay, then randomly select, I'm going to say every K. So this could be 10th, 100th, etc. member from the list. So that's kind of cool. It's not a random sample because the second member of the list probably won't be selected. But you can pick every 10th, every 100th, every 50th, whatever. And that's a systematic sample, very systematic. Okay. And then a convenient sample is obviously you just pick people that are, or pick members that are convenient. Okay, this introduces, this creates selection bias. And ruins your study. How about that? Great enough. Self-selecting samples is when members choose to participate. So that could be a website survey, that's self-selecting. It could be my 8:30 a.m. Statistics class. You guys chose to sign up. You're self-selecting. You're the ones who are deciding to be in my sample. Okay, that also, this is also a convenient sample. So it's just as bad, right? Any questions about that? Convenient sampling is bad. And we list it only because there's a lot of convenient sampling that goes on out there. And we just have a name for it. So you should know, oh, that's a convenient sample, it's no good. Or that's a self-selecting sample, that's no good. Both of them will have selection bias. You guys okay? All right, let's go see if we can get experiments done. And we've got 40 minutes, so yeah, a little less than 15 minutes left. Last thing, experiments. Here, the goal is to gather data to determine the effects of an experimental treatment. The main problem is with experiments is confounding. This is where a given effect has multiple possible causes. Okay, so you can't make a cause and effect statement when there are multiple causes, possible causes, and you don't know which one's the real cause. And sometimes it's multiple causes. Okay, I mean, there's two causes for an effect. Okay, they have to both happen. Okay, so that's confounding. And examples of confounding. Here's one: wine drinkers. Sorry, moderate wine drinkers live longer. Okay, but also well, I gotta say moderate every time I say this. Moderate wine drinkers tend to be wealthier. More educated. Have better jobs, whatever that means. And better health care. If I was to pick one of these, I'd pick the better healthcare for causing their longer life. So we don't know why they live longer. That makes sense? I'd like to be able to say, you know what, you should drink a moderate amount of wine every night and you'll live longer. I'd like to be able to say that. But I actually don't know that it's true. Okay. I think if you are a wine drinker, that you probably have better health care. Not always, but usually. And if that's the case, then maybe you're living longer because you get to go to the doctor when you're sick. Any ideas?
I'm for the wine every day, but I don't do it. So I'll start that experiment.
Yeah. We could do a controlled experiment, but it's going to take a long time to have answers to questions. You really have to have people drinking wine moderately for decades, probably, before you'd be able to finally answer the question. We've known for a long time that wine, and by a long time, I mean for maybe 10 years, we've known that moderate wine drinkers can live a little longer, but we don't know why. We don't have the controlled experiments on that.
Wasn't it? They were saying red wine.
They said red wine, then they started with white, then they went to red, then they said, well, actually beer is good too. So it depends on which study you've heard. Okay, it changes. Nobody's saying they're not true, but none of these have all been observational studies where you can't make cause and effect conclusions. Okay. Now the placebo effect is an important source of confounding. That's where we get better, not because of a treatment, we don't know why. We are confounded. Remember, confounding is where there's an effect, but you don't know what the cause is. So the power of the placebo, it's been shown many times through many studies that taking a placebo, which is just a pill with maybe you could take a tablet that just has something that doesn't have any health effect in it, whatever that is. I don't want to say sugar because sugar might have a health effect, right? But it could be starch. I don't know if it's starch or whatever. Basically a pill that doesn't do anything. Okay, that's a placebo, or an injection, like I said, the placebo, an injection with salt water. Doesn't do anything. Okay, it's been shown many times that patients get better from placebos. More than if they hadn't taken a placebo. Now you can try and come up with an explanation for that, but it's
Mental.
Huh?
It's all mental.
Oh gosh, dang it! The faster I try to write, the worse I get. we don't really try to explain the placebo effect because it's sort of mysterious. Nobody really understands why belief in a treatment can be a treatment itself, but it can. And sometimes very effective. I wouldn't give a placebo for cancer. I think if I was a doctor who gave placebo for cancer, I probably ought to lose my license. You follow me on this? So it sort of depends on the context. But if it's for like migraine headaches, those placebos have been effective for migraine headaches. And sometimes if you think it's a real medication, it can be as powerful. A placebo can be as powerful as a medication that you think is a placebo. Do you hear that? The placebo effect can be as powerful as real medication that you don't believe in. The most powerful thing is a medication that works that you also believe in. You got it? So what you really want is both the real effect of the medication and the belief, which is the placebo effect. So even though it's not a placebo, you could still have a placebo effect by believing. You got it? So let's go on. So how do we do experiments? It says we apply different treatments to similar experimental groups. Why is it important that groups are similar? So that there are no alternate explanations besides the treatments for an effect. Let's say so that an effect has no explanation other than the treatment. Okay. Treatment groups receive real treatment. Except for that's not how you spell receive. Control groups receive placebos or nothing at all. Some things don't have a placebo. If you're doing like social science experiments, you might want to compare students. You might divide a group of students who are taking the SAT into two groups randomly, and tell one group when they write their essay for the SAT to use cursive writing, and the other group they write in block letters, no cursive. Okay. So you've got two groups. Both of them have a treatment, really. One of them is cursive writing, the other one is block writing. Okay. Is there a placebo here? I don't think so. They have to write. Okay. Is there a control? I don't know. Maybe you could call the block letters a control. I don't know. It doesn't matter. The point is that in the end, the people with cursive writing get higher scores on average. Oh, wow. That's amazing. So you get the idea. I don't think there's a placebo there. So similar groups are created through random assignment. So this could be through a random coin toss or other random process. We need to divide people randomly. Okay, this tends to make the group similar. Okay, why is it important to use a placebo? Groups are different if they aren't both taking a pill. Okay. They have to have the same mental state or they're different. Okay. They shouldn't be different. Okay. We need them to both experience the same thing if we can. Okay. Do experiments need random samples? This is less important. But our primary goal is to infer about a treatment or a cause and effect. So is to infer about cause and effect. Okay. Not a population. Still, representative samples should be attempted. It's like we knew that these COVID vaccines were working pretty well, but they haven't included children. So does this represent all people? No, it doesn't. You can't safely know what's going to happen when you give a vaccine to children if they haven't been represented. Right? So they were good experiments, and you can still make inferences about adults, cause and effect inferences, but they can't be applied to children because children still haven't been represented yet. They're starting now, but that was a lower priority. Should patients in a control group know they are getting a placebo, which is called blinding? The answer is no. They should not know they're getting a placebo. Otherwise, you're going to destroy the placebo effect. And we want both groups to experience a placebo effect so that they're the same. And finally, let's just finish it up with this last question. It says, should practitioners know who's getting a placebo? That's called double blinding. No, they should not know. We want them to be actors. We want them to act the same as if the medication works for both groups. They need to act like the placebo is the real thing. And that's helpful if they don't know who's getting the placebo. You got it? So let's leave it at that. I'll kind of pick up on this again next week. You can go ahead and start your homework for chapter 1. There was just a little bit left here, just 3 items. And I'll address those real quickly next week. All right, so I'm going to do my office hour. It'll take me 5 minutes to get to that. And if you guys need to see me or ask questions, you would leave this Zoom meeting, go back to the syllabus and pop into the Zoom meeting for my office hour. And again, I'll be there in 5 minutes. Okay, it's been great working with you guys, and happy to talk to you in my office hour. See you later.
Thank you, Scott.
Okay, so now we're looking at this problem of when there's too much variability in an experimental group, it can be difficult to see differences between groups. And so the solution to that is usually blocking. So if there's just too much variation, let's say you've got men and women in your treatment group or your control group, and you're getting these large amounts of variation. And the idea with variation is it's directly proportional to error. So if you can cut the variation in half, you'll cut the error in half as well. And so blocking is where you just create natural subgroups where people with similar characteristics are put together. And that causes less variability within each group. And again, less variability just means less error. So blocking is a really important tool that can minimize error and make it easier to see differences between control groups and treatment groups. Any questions about that?
So you
yeah, go
said
ahead.
variability, the less variability there is, the less room for error.
Yeah, I mean, your estimates, you're trying to compute an estimate of something from a population. Estimates will always be better when you're working with data that's less variable. Now, you can't control how variable one group is. Let's say you're looking at men over 50. Okay, you can't control the variability within that group, but you will create added variability if you put the men and the women over 50 together. Okay, does that make sense? And so
Yes.
so any statistics you measure from that larger group will have larger margins for error because there's more variability.
Thank you.
Okay, and it's just harder. Again, statistics is always about finding that special exceptional case, especially in experiments and studies where we compare two variables to see that one is influencing the other. It's hard to say, oh, this influence is significant if it has a huge margin for error. Okay. Now, let's read this one. It says, example, testing. We're testing a new medication in pill form. So we're concerned about variability among gender and age groups. So it says design experimental groups and blocks. So we're concerned about variability. I guess we need to separate the men and the women, but we should probably also create age groups. So what if I did like an age grouping? And I imagine these are adults, so we could do 20 to 29, 30 to 39, 40 to 49, 50 to 59. So you see how I'm going to make groups with all these age groups. Each one of these will have less variability. We could say 70 plus on the last one, maybe. And I don't know. And then we're going to need the women in one group and the men in another group. Okay, and then let's just spread these out a little bit. So pardon me for a sec. Okay, so each one of these, this is a lot of groups. You have to keep in mind that the more you divide your groups up, the fewer people will be in your groups. So there's a sort of a counterpoint. We're saying making these things which we call blocks will help minimize variability, which is a good thing, but it will also reduce the number of people in each group. So smaller groups are harder to make good conclusions with. So we'll have, but regardless, with each one, within each of these blocks, we're going to have to do a control
Out.
and treatment group. I think I'll do a slash. That makes more sense to me. So you see that each one of these blocks has two groups. Does that make sense to everybody? So this is basically, it's a pretty complicated study if I'm going to make blocks like this. This is many, many groups.
Professor, would this be stratified sampling?
Well, it's not really any of those. I hear what you're saying. Sampling, stratified sampling is how you're getting your group, your big group to begin with. Now, you're with sampling, you're choosing from the population to get a representative sample, and you might want to do this here. But with blocking, you're taking the sample you already have and chopping it up.
Oh, okay.
You see the difference?
Yeah.
And we only do blocking in experiments, and sampling can be for sampling methods are we're generally talking about observational studies there. So, but I can see how, yeah, we're creating groups, but here these are sample groups, and with stratified sampling, those are population groups. Okay, so difficult. What if researchers come up with a conclusion? I think this is the last thing. Researchers are coming up with a conclusion that other independent researchers can't repeat, which is called replication. If other, researchers, oh God, I can't write today. Can't repeat the results of your study. It will be discredited. Meaning people will realize you were wrong. So that's a motivation to not be wrong and to maybe be a little bit more careful about how you're doing your study, so that you get legitimate results. Sometimes things go wrong and there's nothing you can do about it. And you just have to remember, we're working with samples. And whenever you work with samples, sometimes you'll get skewed data that will lead to the wrong conclusion. So, no worries. It's a little disappointing. You do your best, but in the end, you generally, if it's an important study, someone's going to try and replicate it. Maybe first comment I'd make is the one that I just heard the other day in the New York Times was talking about a guy that I'd heard about years ago, maybe like 2 years ago, not a lot of years ago, who was, I don't know if you guys, how up you are on some of these bacterial infections with what they're calling superbugs, basically bacteria that just aren't dying from the normal antibiotics. And so people that get bacterial infections with some of these really difficult to kill bacteria, sometimes the infections go deep and create a condition called sepsis, which is basically where your bloodstream has infection running through it, and you may lose limbs because of it. And there was a doctor who was recording big results with his people that he was seeing by just, I think he was doing the standard antibiotic treatments, but he was also just putting huge doses of vitamin C in the patients and saying, you know, for whatever reason, that the vitamin C coupled with the antibiotics, he was having like 80% effectiveness. Something amazing, amazingly good given the real hard times that we're having, you know, getting sepsis under control. And so that was in a lot of newspapers and whatnot. And then, and now 2 years later, I'm seeing an article that just basically says nobody else can repeat it. So there was this one doctor who was putting out a lot of great, exciting info about using vitamin C to knock down sepsis. And in the end, he's the only one that got those results. So, you know, he was famous for a little while, but I think his fame has been revoked and he's back to the drawing board, maybe a little embarrassed, you know, because this thing's just not working. You know, I think he was honest in saying, you know, we don't know why we're not claiming this. You know, he wasn't going to make a ton of money off of it because you can buy vitamin C cheap, right? So, but definitely without replication, that sort of discredits the study. Any questions about that? Another thing maybe that's worth mentioning is the social sciences are really interesting because there's always some new study. Because basically what you have, there's just a lot of people working on their PhDs. And when you work on a PhD, you kind of have to come up with something new when you do your dissertation. And something, you know, it doesn't have to be new. You have to either prove something or like disprove something, you know. So disproving is probably easier than proving something. Showing something works, showing something doesn't work, definitely not as exciting. But that, you know, it's research. And but one of the things that's been really interesting with social science that they've really been bringing to the fore is just that in medical studies, replication is sort of like always important. In like if you do scientific like physics and chemistry and whatever types of experiments, I think replication people try to replicate what they see. I remember the big fuss about cold fusion, you know, maybe 20 years ago, where people were trying to make nuclear reactors that were relatively cold so that you could make safer electricity without such dangerous radioactive sorts of emissions. And you know, back in those days, we had one researcher who had claimed to have cold fusion figured out. It was the same thing; nobody could replicate it, and so that was just a huge embarrassment, I think, and a big letdown because, you know, we really do need safe energy. That should be balanced with cold fusion is sort of back again, and there's all kinds of plans that are being drawn up for small nuclear power plants that are small and safe. So I don't think the book is closed, but at the time, the methods that were described just couldn't be replicated. So what what's more concerning is that in the social sciences, now I'm talking like psychology and sociology and, social sciences, those guys are getting PhDs too. But almost nobody tries to replicate studies in the social sciences. There'll be a paper, it comes out, it makes a big, maybe it makes it into the news. And, but there's never a follow-up where someone tries to replicate it. So that's one of the big concerns about the social science research that's out there right now, is that what we really need is to develop a sort of a machine that just reviews research to make sure that it's reliable and it can be replicated in the social sciences, not just medicine, right? So, it's just one of those things where medicine is so much higher stakes than almost any other type of research that goes on, because we have people, we're obviously trying to help people's lives and sometimes save their lives. Okay, so I think that's the last of that topic. I'm going to stop the recording. This little bit will